Okay, so let me begin by, we have discussed the definitions of groups, subgroups, and I think the basic group theory is we have covered it to some extent. So today I will try to go over to what is called the group representation theory. Okay, so you can see the presentation screen, right?
Yes, sir.
Okay, so group representation theory is very useful because all the applications of group theory is only through this group representation. Now, so let us say that we have a group. Okay, so let G be a group. Okay, then let V be some vector space. This vector space and this group doesn't have to have any relation at this moment. So we have already discussed at length about vector spaces in the other course. So since we have done it, I will borrow that knowledge. So let V be a vector space. Okay. Then we define a representation. We define a representation denoted by B of group E on vector space E such that E of G is a map from V to itself. It's a map from V to itself. It's a self map on V for all G in G. Okay, for every element in G, there will be a linear transformation from V to V itself for all G in G. And it has to, of course, satisfy that D of Gi Dj is equal to D of Gi into D of G. That means this mapping preserves the group multiplication theory. This mapping preserves the group multiplication theory. Okay, and notice that if you have, suppose you take D of E. Okay, what will be D of E? E of E. So where this so this has to be, and of course I want you to understand that so the basic operation can be different here, because here this is group binary operation or binary composition. Okay, whereas this is an operation between elements elements of. Okay, so this has to be, depending on this operation, there will be some identity in this. Okay, so for example, if you say that, so for example, let this V be equal to the three-dimensional Euclidean space. Let's say V is equal to R3. That means the vector space that I am considering is equal to X, Y, Z, such that X, Y, Z are real numbers. So this is the vector space that I am considering. Okay, then what happens? D of G is a linear transformation from V to V. Okay, so V to V. That implies D of G is a 3 by 3 matrix. A 3 by 3 matrix. Because a linear transformation from vector space to vector space is a 3 by 3 matrix. And this is true for all G. That means for every group element, there will be a 3 by 3 matrix. Okay, so the representation is a mapping from G to V. That means it's a 3 by 3 matrix. So suppose if I have a group G, let's say it has an element G1, G2, G3, etc., etc. Let's say Gn, such that order of the group is equal to n. Order of the group is equal to n. Then the representation, okay, will have, so the group representation D of G on V. Okay. So these three things we are always. So what is the representation of what group and on what vector space? So D of G on V is basically, I have D of G1, D of G2, etc. D of Gn. Okay, so this set. Okay, so this is what we call as D of G. Okay, is this is a set of n 3 by 3 matrices. Okay, n 3 by 3 matrices. Now, when we say that D of Gi Gj is equal to D of Gi into D of Gj. Suppose when I write like this, now this is group composition. Okay, group binary composition. Correct? And what is this? This is basically matrix multiplication. Matrix multiplication. So the operations are different, but group multiplication table is preserved. Okay, so so that is, now if you want to ask a question, what is D of E for an identity element in G? This has to be an identity matrix. Okay, it has to be an identity matrix. And now if you ask what is D of some GI inverse. It has to be G of GI, the inverse of that matrix. That is inverse of 3 by 3 matrix G of GI. Okay, so this is how we define a representation. So what is the important ingredients of this definition? You should have a group, and then you should have a vector space. Now a representation of group on vector space V is a self map on V for every group element. If there are n number of group elements, there will be n number of such maps. So a map essentially is a transformation or a linear transformation. So it will be a matrix. Okay. So if you have n-dimensional vector space, you have n by n matrix. Okay. So you have to say that you can talk about the dimension of the representation is the dimension of the vector space. Dimension of the vector space. Vector space V on which is defined. So if it is an n-dimensional vector space, then you have a n by n matrix. So the dimension of that representation is called n. Okay. So these are the concepts that are involved in definition of a representation. Okay. Any questions about the definition?
Excuse me, sir.
Yeah.
So here the mapping from V to B, like the vector space to vector space, is doing the same thing what domain to domain does in a real function.
Yes. See, here V is a vector space, and hence this map is a linear transformation. But map is same. Map is so the basic definition of map is same.
Okay, sir. And sir, like why in all, like whether in all cases the matrix multiplication will come, like can't we assume any cases where the matrix multiplication is not involved?
So what I'm trying to say is that when you take a vector space uh, where this linear transformation can be rewritten as a matrix, then this is a matrix multiplication. Okay. You can also talk about uh, certain self maps where we not from a vector space but from a general set. Okay, let's say you have a set X, and then you can define for each group element you can define a map from X to X. Okay, that is not called representation. Sometimes it is called a realization. So one can have a group realization on any set, but if the set is a vector space, then it becomes a group representation.
Okay, so then we will take only in matrix form, because I am a bit confused, because like suppose if a set exists, a set of a real number, so that set of real number can exist other than in a matrix form.
Correct.
So what if I didn't do that in a matrix form?
No, if your vector space is set of real numbers, then also it will be a matrix, but it's a one by one matrix. It's just a number, right? If it's a set of real numbers, then it is just a one by one matrix.
Sir, if we will take matrices, then there will be a limitation of taking non-singular matrices. But as we are considering the inverse of the matrix, so we
Correct.
can take.
Yeah, you can't take singular matrix.
Then, sir, we should mention there that we are taking only n 3 by 3 non-singular matrices.
No, see, I'm not taking all 3 by 3 matrices. No, I am saying that I am going to identify those matrices. And once I say that this group multiplication has to be preserved, then that automatically restricts our choice of matrices. I don't have to explicitly put it there. It is contained in the group. It is contained in this particular expression. Because if I put GI inverse, I get identity here, right? But identity is mapped onto identity matrix, so that means DI. This has to be inverse of this. So what I'm trying to say is that if you consider D of some GI and GI inverse, so that according to the definition, that it is D of GI into D of GI inverse, correct? But this is essentially D of EI. This is D of E. That is equal to this. That means what? D of E is equal to identity matrix. That means this has to be equal to identity matrix, which means D of GI inverse is equal to D of GI, the whole inverse. So this follows from that. So I don't. The moment I say that this has to be preserving group multiplication table, that means we are only entitled to take non-singular matrices. You don't have to mention that explicitly. Is it clear?
Yes, sir.
Okay. So there are two levels at which I want you to appreciate this one. That is, okay, you may wonder why we should consider the vector space. Okay, so that is one question which, if you have in mind, why should we bring the vector space? Okay, so let's try to write down certain examples. So let us take some examples. Okay, let's take an example. So the example that I'm going to look at is that particular group which we have already which we have done it earlier. That is the symmetry group of a triangle. Okay. So I called that as C3D, right? Called it as C3D, which has got these elements: identity, C3, C32, and then there are sigma 1, sigma 2. Okay. Now, suppose consider V is equal to R2. That means a two-dimensional vector space. A two-dimensional vector space. So what will be the matrices corresponding to each one of these elements? So representation of G on V are a set of 2 by 2 matrices. 2 by 2 matrices. So let us try to build that set. Now, first thing, identity has to be an identity matrix. So identity is related to 1, 0, 0, 1. A 2 by 2 identity matrix. Now we know that if you have an XY plane,
Excuse me, sir.
yes,
Sir, some of our students are trying to join.
I don't know why are they not able to join. So what they want admission?
Yeah, that's what they asked. They were trying for some time, I think.
Okay, I have got one. But why do you require this? I mean, are they from? All of you did not ask me, right, before joining?
That I don't know, sir.
Sir, I think they are using some other mail ID, sir. You might have sent the link to their given mail ID. They might try to join from some
So
other.
then please use that mail ID. No, it's convenient. Otherwise, it will disturb the flow of the lecture. Because when I am presenting, I will not see if somebody is waiting. Then somebody, like what you have done, you have to prompt, and then I have to stop the lecture and then do this admission.
Okay, sir, thank you.
So I request you to please join with the same mail ID to which I send the invitation. Then I think you don't have to wait. Okay. So identity element. Now you know that suppose if I have a vector like this, whose components are x comma y. Okay, whose components are x comma y, and let us say this can be also written as the magnitude of this vector and then this theta. So we know that this x can be written as r cos theta and y can be written as r sin theta. Correct? This is something which you might have known, but I'm just doing it just for completeness sake. Now suppose if I rotate this vector. So I have rotated this vector by an angle phi about z axis. I rotated in this direction about an angle phi. Now this will have a different coordinates, x prime, y prime. Correct? It will have different coordinates, but the magnitude will not change. So I will have x prime is equal to r cos theta plus phi, and y prime is equal to r sin theta plus phi. Okay, so now you know this trigonometric identity that you have x prime is equal to r cos theta cos phi. Cos theta plus phi is cos theta cos phi minus sin theta sin phi. Okay. Similarly, I can write down y prime is equal to r sin theta cos phi plus cos theta sin phi. Okay. Now you can immediately see that this r cos theta is x, r sin theta is y. So I can show that this implies this x prime and y prime, if I write it as a column, this is equal to cos phi minus sin phi, sin phi, cos phi, operating on x, y, r into x, y. So this is essentially is a rotation matrix about z-axis by an angle phi. Rotation matrix about z-axis by an angle phi. Now, what is C3 here? C3 is the rotation about z-axis, of course, by an angle 2 pi by 3. 2 pi by 3 is 120 degrees. So you have to ask what is cos 2 pi by 3. Cos 2 pi by 3. Cos 2 pi by 3, you can write it as cos pi minus pi by 3. Okay, which is equal to minus cos pi by 3. Cos pi minus pi by 3 comes in second quadrant. So cos is minus. So it is cos pi by 3. But what is cos pi by 3? Pi by 3 is what? 60. Okay, cos 60 is half. So this is minus half. Okay. Similarly, you can ask what is sine 2 pi by 3. So I can write this as sine pi minus pi by 3. Sine is positive in second quadrant. So sine pi by 3. And sine pi by 3 is basically root 3 by 3. So this equation, this C3 is a matrix like this. Minus half root 3 by minus half minus root 3 by 2 and root 3 by 2 to minus half. So this will be my C3, a vector corresponding to C3. And remember this, a matrix corresponding to C3. Remember that we are not choosing them arbitrarily. We are considering the group action. Okay. Now let us look at the C32. So what is C32? C32 is basically cos 4 pi by 3 minus sine 4 pi by 3 and sine 4 pi by 3 and cos 4 pi by 3. Okay. So what is 4 pi by 3? So cos 4 pi by 3, you can write it as cos pi plus pi by 3. Cos pi plus pi by 3. Cos pi plus pi by 3 is cos, this will be in third quadrant and that is also negative. So minus cos pi by 3. Okay. And similarly, sine 4 pi by 3 is equal to sine pi plus pi by 3. In third quadrant, sine is also negative, so sine minus sine pi by 3. So you see that this is nothing but we have minus half root 3 by 2 minus root 3 by 2 minus half. Okay, so that is your C32. Now you can write down one of these sigmas from the geometry. Okay, so remember that we had this triangle like this. Okay, we have a triangle like this. Z-axis chosen perpendicular to the plane on which I have drawn this figure. Now I can choose one more axis. Okay, I can choose one more axis. So suppose if I choose my let's say y-axis along this. Okay, let's say this is my y-axis. Okay, then this becomes x-axis. So see, if this is your sigma 1, x-axis will change sign. That means my sigma 1 can be written as minus 1, 0, 0, 1. That means y does not change sign and x will change sign. So this can be sigma 1. I cannot write like this other components because other mirror is not along any one of the axes. I can only fix one axis, so I am fixing that to be y-axis to define sigma 1. Now, how do I find the other axis? I have to find out the other axis by using group multiplication table, right? So, for example, if I go back to so if I go back to this group multiplication table, so in the sigma 1 category, when will I get sigma 2? I will get sigma 2 when I multiply sigma 1 with C3 and sigma 1 with C3 2, I will get sigma 3. So I have sigma 2. So sigma 2 is equal to sigma 1 C3. So that is equal to minus 1 0 0 1 into C3. C3 is given by this. That is minus half minus root 3 by 2 root 3 by 2 minus half. So that is basically half root 3 by 2 and root 3 by 2 minus half. So that is the thing for sigma 2. Now let's look at sigma 3. Sigma 3 is sigma 1 C3 2. That is equal to minus 1 0 0 1 2 minus half root 3 by 2 minus root 3 by 2 minus half. So that gives you half minus root 3 by 2 minus root 3 by 2 minus half. Okay. So now I have 2 by 2 matrices for each one of these group element. Okay. So let us
Sir, I couldn't understand how you wrote sigma 1 matrix. Can you repeat once again? Like how do you fix the y and you wrote minus 1 0 0 1?
Yeah. So this triangle is on a plane, right? So triangle is on xy plane, correct? XY plane. So axis can be fixed. So I'm going to choose y-axis along sigma 1 mirror. So that is my choice in this particular case. You could have chosen z-axis, y-axis along sigma 2 also. Then you will get for same matrices, but then your labels will change. I can choose y-axis along sigma 1. So that means what? When sigma 1 is acting on xy, I should get minus xy. X will become minus x, but y will not change. Is that clear? That means what? That means this is like minus 1 0 0 1 acting on xy. Correct? So the sigma 1 action on on a coordinates on xy plane is like this matrix is acting on those coordinates. So I will call that as the matrix for sigma 1. Now suppose I want to find sigma 2. Now sigma 2 is not very simple because since this is my sigma 2, for example, so this is not going to leave any one of the coordinate invariant. Correct? So that is why what I am using is I am going back to the group multiplication table and then trying to find out what is sigma 2 and sigma 3.
That's because sigma 2 will have components along x-axis as well as z-axis.
Correct.
So,
correct.
so only okay.
Yeah.
Understood, sir. Yes.
So so what we are doing here is that, so in summary, a two-dimensional representation, of the group E3 on the vector space R2 is the following. So you have E, you have C3, you have C32, you have sigma 1, sigma 2, and sigma 3. So these are the elements of the group, and so we have 1, 0, 0, 1, and this will be minus half, minus root 3 by 2, root 3 by 2, minus half, and this is minus half, root 3 by 2, minus root 3 by 2, minus half, and this one is minus 1, 0, 0, 1, and this is half, root 3 by 2, root 3 by 2, and minus half, and this one is half, minus root 3 by 2, minus root 3 by 2, minus. So these are the elements that we have as the group representation. Okay, so this is just to tell you how we write down a group representation. Now I can also talk about, like someone was asking this question earlier, we can say that I can choose any vector space. I can choose any vector space. Now let us say choose the vector space. Choose the vector space as simply R. That is set of real numbers. Okay. Then we ask a question. So you can also talk about a representation, right? So we can ask the question: what representation? What representation can we construct for E3V on R, on the vector space R? So one of the trivial representation, okay, so the most trivial representation that I can construct is, so let's say I have E, I have C3, I have C32, sigma 1, sigma 2, sigma 3. Now, since this is R, what will be D of each of the representation? It will be a scalar, 1 by 1 matrix. Okay, so the representation is so since R is a one-dimensional vector space, one-dimensional vector space. The representation is a 1 by 1 matrix. That means it is simply a number. 1 by 1. What numbers can I associate to each one of them? So the most trivial, I called it most trivial because I'm going to call this as 1, this also 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 1. Will it satisfy group multiplication table? Yes, it will satisfy. Okay, this is the most trivial group representation that I can talk about. Okay, so I can say that D of G is equal to 1 for all G in G is the most trivial one-dimensional representation that exists for any group. Okay, so this is one representation. So whatever I have here, 2 by 2 matrices, is a two-dimensional representation. This is one-dimensional representation. Now let us look at this group multiplication table carefully. Okay, so if you look at this group multiplication table, now this block that I have shown here, okay, this EC3C32 block, okay, so this block is actually same as the block here, right? So this block so this block, for example, is same as the block here. So this block and this block are same. In the same way, this block, off diagonally, this block and this block are same. That means if I make a, so the structure is something like this. Suppose if I make a representation, okay. So suppose if I make a representation, so consider another one-dimensional representation. Where E, C3, C32, I will map it to 1, and sigma 1, sigma 2, sigma 3, I will map it to -1. Okay, so if I map like this, then this will also satisfy group multiplication table, because as we have seen, these diagonal blocks are same, these off diagonal blocks are same, correct? So normally if you have 1 minus 1, we will have that structure, right? 1 minus 1, 1 minus 1, this is 1 minus 1 minus 1, 1. So this block and this block will be same, and this block and this block will be same. So you have this structure for that group multiplication table, and hence another one-dimensional representation like this can be constructed. So for this group, I have now constructed some 3 representations. Now I can construct a representation of any arbitrary dimension. Okay, how do I do that? Okay, so now let's say that we will talk about construction of an arbitrary representation. So let's say how to construct a representation. How to construct a representation of a given dimension. Okay, suppose that is the question that we are asking. Now let's say that we are interested in constructing. Let's say we are interested in constructing a three-dimensional representation. Okay, to be specific, let us construct a 3x3 a three-dimensional representation. Three-dimensional representation. So the procedure is something like this. Now, if you look at this, so let us go back to this picture. I mean, this two-dimensional representation, and let us say that for each of this element, okay, for each of this element, what will a vector xy change as? That's what I want to write. So what will be E acting on xy? Simply xy. Correct? Because E is an identity. So that is what it is. That means if you define your x prime y prime as E acting on xy, then that is simply xy. Suppose if you ask x prime y prime and C3 acting on xy. Suppose if you do that, C3 is acting on xy, then that will be equal to what? That will be equal to minus x by 2 minus root 3 by 2 y, root 3 by 2x minus y by 2. So x and y are mixed here for C3. Okay. So this is how x and y will change. So like that, you can find out. Okay, so suppose you have, so let's say your x prime y prime, you can write it as E of g acting on x and y. And for each g, this B of g is different, right? So that means for each group element, the way these x and y mix are different. You understand that, right? Okay, let us say that you are able to do this. Okay, I mean, you can do this, of course. Now consider the following situation. Okay, I did not do this completely. I will request you to do it, this calculation. So now let's say that, so consider a vector like this. All quadratic terms, that means x prime square, x prime y prime, and y prime square. Now, we know, okay, we know how x prime y prime is related. X prime y prime is related to xy for each g in G. Like if it is identity, it is same. If it is C3, then it is like this. C32, it will be in another way. So you know that this relation is like this. So now use that relation. Use that relation to write x prime square, x prime y prime, and y prime square is equal to, you have a 3 by 3 matrix, x square, xy, y square. That is, if you use those relations, substitute for x prime square, x prime, y prime, etc., then you will get a matrix here. So this will be a 3 by 3 matrix, because it's a column vector of 3 elements. It will be 3 by 3 matrix. We use that relation to write it like this. So this is a representation matrix. Representation matrix for that G in. For each G, you have to do this exercise. Then you will get one 3 by 3 matrix for all the group elements. Of course, the identity element, it will always be an identity matrix. Okay. So like this, you can get a set of 3 by 3 matrices, which is called a 3-dimensional representation for this. So I will leave this as an exercise. Okay, so exercise. So complete this calculation. Complete this calculation to construct 3-dimensional representation. 3-dimensional representation of C. Suppose I want 4-dimensional representation. What I should do? Okay. So to construct 4-dimensional representation, start with x prime cube, x prime square y prime, x prime square y prime square, and prime cube x prime y prime square and y prime. Right? So there are 4 elements here, and you write this again the same procedure. You write this a 4 by 4 matrix multiplied with x cube, x square y, xy square, y cube. For each element, you will get a set of 4 by 4 matrices. This is one procedure by which you can construct a dimension of a given, a representation of a given dimension. Okay. Now, is this the only procedure? No, this is not the only procedure, but this is one procedure in which you can construct a representation of an arbitrary dimension. Okay. So this is about how to construct a representation. Okay. Any questions here?
So one small doubt, sir.
Yeah.
So if we want to construct a representation of a group on Q, like the rational numbers, set of rational group of rational numbers, then that will be infinite dimensional vector space.
Correct.
But the numbers are one dimensional, no sir? So how
Number?
can you construct? Hello sir?
Go ahead.
So
So,
if we want to
a vector
construct a
space, vector space.
representation of a group on Q, the group of rational numbers, that
Correct.
is infinite dimensional vector space,
Correct.
but the numbers are one dimensional.
Hmm.
So how can you construct representation?
Yeah, so that's in some sense a pathological example, in the sense that when I am saying that, so the question, I think the interesting question that you are asking is that is it possible that a representation of a group can be constructed on any given vector space?
Yes, sir, but you mentioned that for any given vector space, we can construct representation of a group.
Correct.
So that's why I thought of this example.
Yeah. It's good that you thought of that example, but so your question there is that since it is an infinite dimensional vector space, your representation should be infinite by infinite matrices. Correct?
Yes, sir.
Infinite
Yes.
by infinite matrices, but the elements of the vector space are just numbers.
Yes, sir.
Correct? Yeah. So I think it's a good question, but I think we have to. I honestly, I really don't know the correct answer for this, but let me see that. Let me say that the infinite dimensional nature of this this vector space is coming because of these irrational numbers. Now you have to have some way of representing these irrational numbers in some fashion. So I do not know how, but this is a good question. So we can ask what kind of representations can one construct on this vector space. But honestly, I have not thought about it. But it's a good question.
Okay,
So
thank
let
you,
us
sir.
think about it.
Okay, so you can go ahead.
Sir,
Yeah.
then set of real numbers is also infinite dimensional, sir, isn't it? Why it is one dimensional then? We can have
No,
any number of
no. Set of
real
real
numbers.
numbers on real field is just one
Ah,
dimension.
real numbers or real field is one dimensional.
Yeah.
Similarly, for rational numbers on a field over rational numbers, then it's also one dimensional, isn't it, sir?
But what Debanjan is pointing out is set of real numbers on the field of rational numbers,
Okay.
because there to represent see the number of field variables required to represent an arbitrary vector is what we are calling dimension, right? So if you take some irrational number like square root of 2 or something like that, you require infinitely many rational numbers, and hence the dimension has to be infinity for that vector space. Okay, so this is one question I asked yesterday. Yeah, I think yesterday in the last. I am also getting confused. Probably in the vector space discussion, we asked this question: what is the dimension of the vector space of real set of real numbers defined over what is it? Rational numbers. So what he's asking is, on such a vector space, how do you construct a representation of this group?
Okay.
Yeah. So any other question? Okay. So if there are no questions, let us proceed. We will define a few more concepts. Okay. So first we will define the notion of equivalent representation. Equivalent representation. So let's say that let D of G on V and B prime of G on V prime be two representations. Okay. Then B and B prime are equivalent. B and B prime are equivalent if and only if there exists a map S from V to V prime. There exists a map V to V prime such that V of G is equal to S V prime of G into S inverse. Okay, there exists an invertible map. There exists an invertible map S from V to V prime such that D of G is equal to S dG S inverse for all E in G. That means there should be one S, one transformation S, which similarity transform, or these two are related by a similarity transformation. And now one S should work for all the group elements. Okay, so it's not that for G1 S is different, G2 S is different. There's only one S that should actually relate these two things. Okay, and if no such S exists, D and D prime are unequivalent. D and D prime are unequivalent. If it doesn't exist, then they are unequivalent. Okay, so one way to recognize, or one way to create inequivalent representations is that note that one sure way to produce inequivalent representation is to choose V and V prime of different dimensions. Okay, so if there are different dimensions, then what happens? This S is not a square matrix. It will be a rectangular matrix because V and V prime are different dimensions. Then this will be a rectangular matrix. So then they will not be inequivalent because the inverse concept of inverse itself is not meaningful there. So then those are definitely inequivalent. So if the vector space dimensions are same, then they may be equivalent. Okay, so this is the concept of equivalent definition. Then we have another concept called unitary representation. Unitary or orthogonal. Orthogonal representation. So a representation T of G on V where V is a complex or real vector space. Okay, whenever this is a complex vector space, then we call it unitary representation. Whenever it is a real vector space, we call it orthogonal representation. That is why I am writing explicitly here. V is a complex or real. What do you mean by complex vector space? It's a vector space defined on the field of complex numbers. Real vector space, it is a vector space defined on the field of real numbers. Okay, is said to be unitary or orthogonal if there exists an inner product. There exists an inner product on V in V such that the inner product such that for all x comma y in V, dg x comma dg y, the inner product of these two elements is same as the inner product of these elements for all t in. Okay, if this kind of an inner product exists, then we call that as a unitary representation. So this inner product is called a Hermitian or symmetry. In the real case, it is symmetric. Symmetric inner product. Hermitian inner product or symmetric inner product. Okay, so if that kind of a inner product exists, such that you take that group matrix and then multiply, it is as if you are just taking the inner product of x and y. So then it is called a unitary representation.
Sir,
So, yeah.
one doubt. So it's a symmetric inner product. Does that mean it's not sesquilinear?
It's not
Sesquilinear?
no. See, the sesquilinearity is independent of this, no? Because that
Symmetric
is
means like it's like it's from the left argument is like linear and right argument is antilinear.
correct.
So the
No, it's the other way. From the right, it is linear.
It depends on the conventions.
Yeah. So I'm sure you are asking this, right? Suppose if I have x and alpha y is alpha times xy, and
Yes, sir.
alpha xy is alpha star xy.
It's a bracket notation.
Okay, so this is what you are saying.
Yes, sir. What
Okay.
is symmetric in a product, sir? Means xy is equals to yx bar, no, sir?
Yeah, in general, for complex V, we have x, y is equal to yx star, correct? Xy equal to yx star.
Yes, sir. Yes, sir.
Yeah. So if it is not complex V, if it is real V, then it is xy is same as yx. That is
Yes, sir.
symmetry.
Yes, sir.
Yeah.
For here, like it's xy equal to yx.
Yes. Yes.
Okay, but it can v can be a complex vector space.
Yeah. We can be a complex vector space. Actually, we are going to deal with mostly complex vector spaces. So I could have simply defined as a unitary representation. But then, if you have a vector space where you are defining it over a real field, then we will call the same thing as orthogonal representation. And this inner product is called the Hermitian inner product. If it is orthogonal representation, it is called the symmetric inner product. These are just names.
Okay, sir. Thank you.
Okay, so that is these are the two things that I wanted to define. Now let us try to. Okay, here I think I have to introduce a concept. Okay, so I think I realized that in my discussion on vector spaces I did not talk about it, but let me just introduce this concept. So suppose we have a vector space. So let's say V is a vector space. V is a vector space. Then let U be a subset of V. Okay, that is U is a subset of V. Okay, then U is called a subspace. This is right now only a subset, and we will call this a subspace of V if and only if U is also a vector space. This is somewhat similar to the subgroup that we have done. So a subset of a group is a subgroup if that is also a group. In the same way, a subset of a vector space is a subspace of V if and only if U is also a vector space. That means within the vectors, the set of vectors in U should also satisfy all those axioms of the vector space. Okay, so this is called the vector space. Now, there is a nice theorem. Okay. A subset U of a vector space V, is a subspace of V if and only if U is closed under vector addition and scalar multiplication. So I have written these things in words. That is first condition is closed under vector addition. That means for every u1, so let's call it, for every x comma y in u, x plus y is also in u. This is the closure under vector addition. And second is for every alpha in the field and x in u, we have alpha dot x is also in u. So this is closed under vector addition and closed under scalar multiplication. So if u is closed under vector addition, so actually you have to only look at these two conditions. You don't have to solve all the axioms to show that it's a vector space. Okay, so a similar theorem we talked about in subgroups. So this is something like this. So I will leave this proof for you to write down. Okay, so the exercise, write the proof. Okay, so this is a subspace. Now we can talk about, once we understand subspace. For example, if you say that I have a vector space R3. Okay, so I have vector space R3, which is given by this x, y, z, such that x, y, z are in R. So this is a three-dimensional vector space. Now let's consider R2. R2 is what? Simply x, y, and put 0 here, such that x, y in R. Okay, so this is a subspace of this, because this is also a vector space, and this is a subspace of this. Okay, so R2 is a subspace, so it's trivial, subspace of R2. Okay, so this is just an example. Now we have now we are ready to define an important concept of the representation theory. Okay, so that is what we call as, so after we define this subspace, we will now talk about reducible and irreducible representations. Reducible and irreducible representation. Okay, so let us say that so consider a representation B of C on a vector space V. consider a representative B of G on a vector space. Okay. Now, if there exists a subspace, I will call it as V1 of V, such that for all x in V1, that means for all vectors in V1, d of Gx is also in V1 for all G in. That means I start with x and then I operate with group matrix or the matrix associated with the group element. I will remain in V1. Okay. Then we say that V1 is an invariant subspace. An invariant subspace under the action of group G. Okay, we will say that V1 is an invariant subspace under the action of group G. Okay. If such a if there exists something such that it happens, we say that V1. Okay, so if such an invariant subspace, exists, for V, then the representation V is called a reducible representation. A reducible representation. Called a reducible representation. If no such invariant subspace exists, no such invariant subspace exists, B is called an irreducible representation. Okay, so now we have to see under the action of this group whether there exists an invariant subspace. If it is so, then we say it is reducible. If no such invariant subspace exists, then we say it is an irreducible representation.
Sir,
Now,
can you explain this? Can you explain the same sentences in example? It will be much clearer, if possible.
okay. Let us try to. Let's say that. So just to think of an example. Let's say that D of G. Okay, so let's say that E is 3-dimensional. Let's say, for an argument's sake. Okay. Now we say that D of G has to be a 3x3 matrix. It implies D of G is 3x3 matrix. 3x3 matrix for all G. But let's say that this D of G has got a form like this. Okay, it has got a form like this. What is this form? So let us say this has some kind of a x of G. So let's say this is 2x2 block. Okay. So this is a 2x2 matrix. And then there is some 0 here and 0 here and some y of G here. Okay. So let's say x of G is a 2x2 matrix. Is a 2x2 matrix. Okay. 2x2 matrix. Maybe I don't even have to have 0 here. So I can have let's say some z. Now this x, z, y, this can be some, z is a number, y is a number, x is a 2x2 matrix. Suppose, and these are different because x of G, I said G is there in there. So different G basically on 3 dimension, right? So suppose you consider vectors like this. So consider vectors like this. Suppose you take this D of G, when you act this on x, y, 0. Suppose you act this on x, y, 0, then what happens? You are going to have this x of G, 0. This is a 2x2 block. And then you have some, I can have, actually I should have two numbers here. So let's say some Z1 of G and Z2 of G and some Y of G like that. So I have Z1 of G, Z2 of G and Y of G. And there's a 0 here. So if I have this X, Y, 0, then what will I get? I will get let's into this one. Yeah, so this will be equal to what? This will be equal to this x of G acting on xy, and then I will have 0, 0, and then this will be Z1 of G into x, Z2 of G into y. Okay, and
0,
yeah,
0, 0.
0. Okay, so now what happens is that this form is going to be the same as this, right? Of course, y of G is there, but that. So can I say that? Sorry, I think this is. x of g. Okay, I think I made a mistake here. So this is a 3 by 3 matrix and this is a column vector. So I should get a column vector here, right? So what is that column vector? That column vector is going to be, maybe I think I should explicitly write it. So let me say my d of g is equal to, let's write this matrix like this. So let us say d11 of g, d12 of g, 0, d21 of g, d22 of g, 0, and d31 of g, d32 of g, and d33 of g. Okay, suppose it is like this. Now I can say that this d of g on, suppose I take d of g acting on x, y, 0, so that will be equal to this quantity, this matrix acting on x, y, 0. So that will be equal to what? That will be equal to d11 of g into x plus d12 of g into y. That's the first element. And second element, okay, so I think I have to be careful here. So I must not write these elements. Okay, so I must write 0, 0 here, and maybe I can write d13 of g and d23 of g. Okay, so then the next one is d21 of g into x plus d22 of g into y. And lastly, I will have 0 here. So that means you are taking a vector in R2 and then you are getting another vector in R2. What does that mean? This is true for all G. Whatever is your G, if this is the structure of your matrix, that means these two elements are 0 for all G. In that case, you will have a vector in R2 will remain in R2. Then we say that this vector space x, y, 0 such that x comma y in R. Okay, this is an invariant subspace. Invariant subspace of this vector space, that is x, y, z, such that x, y, z is equal to in R. Okay, for this vector space under the group action. Okay, so this is what I am trying to say. So that means you can have an invariant subspace. If you can have an invariant subspace, then we say that this three-dimensional representation. So this implies this three-dimensional representation is reducible. If we cannot find such invariant subspace, then we say it is irreducible. Now you may wonder that how do we know whether this representation is in this form? I am just giving an example. But when you actually find the representation, like suppose I told you here that if you want to find a three-dimensional representation, you take this x prime square, x prime, y prime square like this. When you construct a three-dimensional representation, if that has this structure, then you know that it is reducible. Okay, so this is what it is. Now we can further say that, so suppose let us say that a representation, so let's define another concept. Okay, maybe I'll just define this concept and then do it. So the next definition is decomposable. Decomposable representation. Okay. So let D be a reducible representation. Of G on some vector space. What does that mean? That implies there exists an invariant subspace, V1 of V under the action of this G. Okay, that is what it means. Now, if there exists another invariant subspace, call it V2 of V, such that V can be written as V1 direct sum of V2. That means I can consider this as a direct sum of these two vector spaces. Then E is said to be decomposable. And if no such V2 exists, then E is indecomposable. For example, in this particular case, let us try to look at the following situation. So we talked about a subspace like this. Suppose now you consider this situation. Suppose I consider a vector space which is 0, 0, Z, such that Z is in R. Okay, suppose you take this space. Now what happens if I use the same matrix with 0, 0, Z? That will be equal to 0, 0. That will be equal to, no. So what will that be equal to? So this is 0 into 0, and this will be D13Z, right? So D13Z, G into Z, D23 of G into Z, and D33 of G into Z. Okay, So I am taking 0, 0, z, but this is not giving me 0, 0 into some element. I am getting all elements. So that means what? This 0, 0, z. So this is not invariant. So this is an example of a representation which is reducible but not decomposable. Okay, it is reducible but not decomposable. But imagine that you have got a situation where these two elements d13 and d23 are also 0. Okay, so let's say that this is also 0 and this is also 0. In that case, what happens? D13 is 0, D33 is 0, then this will be 0, 0, D33Z. This is also invariant, and hence it becomes decomposable. So one can understand that a reducible and decomposable means the matrix corresponding to that representation should be in a block diagonal form. That means off diagonally elements should not be there. If off diagonal elements are there, then it can be reducible, but it is not decomposable, as we have seen here. So in summary, we have a representation a representation of V on V can be reducible, or it can be irreducible. When do we say it is reducible? If an invariant subspace V1 of V exists under the action of G, and no such invariant subspace okay. And at the next level, we have a reducible representation can be decomposable or it can be indecomposable. That means decomposable means there exists another invariant subspace V2 of V such that V can be written as V1 direct sum V. Okay, indecomposable, no such V2 exists. Okay, so these are the types of representations that we have. Okay, I will stop here. If there are questions, you can ask.
Sir?
Yeah.
So this decomposability you have also mentioned using Decker map. So is that related to the constant energy surface indecomposable? So is that related, sir?
No, it's yeah, it is. So basically, there the indecomposability is by the dynamics. Here, the indecomposability is by the action of this group. Okay,
Both are
so you can
different.
also consider the dynamics as a group. So in that sense, you can relate.
Okay, sir. No, both are different.
Yeah, yeah.
Okay.
Excuse me, sir.
Yeah.
Sir, I'm sorry, but I couldn't understand like what this dimension of representation means. Like, I got the mathematical idea like how to find it, but I can't understand how it is different from dimension of vector space.
That is
And
same as the
actually,
dimension of the vector space. See, the dimension of a representation is equal to the dimension of vector space.
is it like we are decomposing group like as in like vector space be if we want to space in different coordinates or different bases, so we need a dimension. So is it same like for group also?
No, no. See, what I'm trying to say is that let's say there are some okay, let's say there are some group operations. So some symmetry operations, like in C3 case that we have seen, there's a particular symmetry operation has certain invariance of the geometrical structure or a molecular structure that you have at hand. Now I want to understand how this symmetry is to be operated in different vector spaces. 3-dimensional vector space, 4-dimensional vector space, 10-dimensional vector space. Now I want to represent this, or I want to project this group into a vector space. Now how do I do that? I have to define some animals in that vector space, or some operators, or some transformation on that vector space, such that there is a correspondence between the group element and then that vector space, or the transformation on the vector space. So they are like, in this case, linear transformation is a matrix. So I have a vector space. So now what happens is that the vectors of the vector space are transformed based on this group multiplication table of this group with this representation. So it is like the action of this group on the vectors of the vector space. Now you give me any vector space, I will be able to work with the action of this group on that vector space by defining an appropriate representation. So different vector spaces will have different representations, and the dimension of the representation is defined as the dimension of vector space on which this representation is defined as a self map.
Okay, sir, I got this idea, sir.
Okay, so let me also tell you that this representation theory is, I mean, considered to be little complex, but of course, there is no substitute for hard work and thinking. So right now in the first lecture, if you are not understanding, you should not get discouraged, but you should not leave it also, because if you persist, you will understand. It's very important, and a lot of difference it makes if you understand these things. So my request will be that you go back to it again and again and again, and then try to collect your doubts, questions, and things like that, so that we will be able to address them if required. But don't give up. I mean, it's tough, but not undoable.
Sir.
Yeah.
Hello, sir.
Yes. Yes.
I am not able to write the last part, sir. So, sir, scroll down, please.
The stable part, or?
Yes, sir. Is it?
Sir, the
Hello,
screen has
sir.
disappeared.